Okay, so I had one more assignment planned for you, then I'm going to end up giving that might become extra credit just because people are behind, so it might be easier for you guys to do an extra quiz. And I don't think I'm going to add to the quizzes, but I think in general quizzes might be easier to deal with. So we have pretty much finished all the, if you will, systems component of the course. So we've looked at a bunch of mechanisms, and they're sometimes hard to master so that you can use them easily. Um, and we are going to now go into more algorithmic components. So I won't call it theory, but I'll call it algorithmic. Theory typically means proofs. So we won't be doing proofs, but we will look at techniques and algorithms. And your last required project, which is yet to be given, will involve implementing some simple algorithms that I'm going to talk about. So the problem we are looking at is consensus. Okay, and that's a term you will find um, in a lot of distributed computing literature. And here's the definition of it. We said earlier that in a distributed system there are coupled processes, so that one process can influence the competition of another process. And in the consensus problem, we assume that the coupled processes replicate some state. And the replicated state can consist of multiple objects. So we have two processes here, P1 and P2. In general, you can have an arbitrary number of processes. And we have two pieces of replicated state, O1 and O2. And let's assume that there's a way to write to the state, change the state and read the state. Okay? In not all scenarios will we have both reading and writing at each site, at each process. So that's the context, that we have some replicated state and we want some guarantees about the values that are in different processes. And the guarantee that we want is consensus. And we can say that if we take any piece of replicated state, OK, and take any two paired processes, Pi and Pj, then if we try to read the value of that object, replicated object in process Pi, then that value should be equal to the value in process Pj. Okay, so if process Pi and Pj are P1 and P2, then P1.O1.get should be the same as P2.O1.get. And similarly, if we are looking at O2, then P1.O2.get should be equal to P2.O2.get. Okay. Either that should be true, or the get function should say, sorry, I can't tell you, the state is unstable, it's undefined. So take no action based on the value of the state. Okay. So either the get function returns an undefined value, or the get functions on corresponding objects and corresponding processes all return the same value. The first question we'll start off diving right away into is why undefined? I mean, it makes sense for them all to return the same value, but why would you accept the get functions returning undefined in the various processes? Okay. So why undefined? Achieving consistency can take time. Okay. Even if you assume data transfer at the speed of light, that can still take time, and data don't go at the speed of light. You go through routers. It takes time for it to reach another machine, from that into the buffers, from buffers into the process. The process takes time to change things. And so indeed, the value can be in flux, as David said. So we will go and allow it to be undefined. Okay. So here's, we're going to look at many examples of consistency that we see in ordinary life. But let's take something from, let's assume that the processes are replaced by human beings. So let's go and take a real world analogy that's not computer based. So let's say that because of lockdown, someone, me or some student, proposes a course change to accommodate lockdown. Okay? So we have gone and started off the course by saying these are the rules, and suddenly the context changes. So we want the rules to be changed. Okay? And we go and decide to have a vote. And the 15 students right now in class, they get to vote. There's 26 students, I think. So since they're not in class, they don't get to vote. So the ones who get to vote are, we'll call acceptors. Okay, and in your assignments, you've noticed that we have had phrases like proposal made, proposal accepted. I don't remember if we have proposal accepted or not, but we certainly have proposal learned. Okay, so the next stage is learners. Okay, so everybody in class must learn about it. Okay, we have to make sure that everybody's on the same page. Okay, and everyone should know that everyone else knows about the vote. Until we know this, we don't want to take any action based on this course change. Okay, so if somebody goes and says, what's the new syllabus? Either we give the old value, old status, or we go and say, sorry, it's in flux, and um, make no decisions based on this. So that gives you a motivation for the problem definition. So there should be no misunderstanding. Either the vote is undecided or everybody will reason the same result. So this is a human analogy. Let's look at the computer world now, which is the world we are living in today. So let's look at familiar computer-based real-world examples, not human-based. And there's many different examples you guys should be able to come up with. But let's constrain right now the world and say, okay, we're assuming that there's one reader and multiple writers. Okay, so we are writers and readers have replicated state. And actually, I should change this afterwards. Let's assume that there's only one writer and one reader. Okay? The reader and writer have replicated state, but not all writers have to have so two different writers don't have replicated state. Okay, so let's assume that these are independent writers. So the state of the state in each writer is replicated in the reader, but the state of each writer is not replicated in the different writers. Okay, let's go and take that example. So that's why I'm not showing you any arrows between writers, and I'm not showing you any arrows from the reader back to the writers. Okay. So can you think of some familiar real-world example where um, um, this kind of architecture exists? Yeah, where you do want the guarantee that um, we have consensus on what the replica values have in the reader and the writer. So there is this client, your browser, and you're using the browser to go and enter stuff. And until you save values, the values don't go into your server, which is the Sakai server. Okay? And then, of course, whether you submit or not is a separate issue, and that goes from one state of the server to another state of the server. But you get to make a transaction, and if you don't want things to be saved, you don't save them. And I'm assuming it's not, I've never taken a quiz in Sakai, but I'm assuming you have to save every now and then, that it doesn't automatically go and take your values and put them in your state. Okay? And you can imagine many such applications. Anytime you use a browser to go and uh, uh, change some state in a server, essentially you're doing this. Okay? So we have multiple independent writers. Okay, I had one client, one server example, and I made it multi-client just so that I wanted a dual of this picture. So let's go to the dual of the picture. But it's very important again that these clients are independent. You could imagine a collaborative text system where you guys are collaboratively taking a quiz, in which case indeed they would be not independent the clients. Okay? But in Sakai, that's supported. So let's go to this dual example that I wanted to go to. A single writer and multiple readers. Um, or at least multiple readers. Think of that. Maybe you want to think of multiple writers writing to the. So maybe you want to think of some processes here too, if you want to make it more concrete. But part of the architecture is that a writer is going to multiple readers. The writer may be receiving information from multiple writers, multiple other writers. So that is something that's orthogonal to what I'm talking about right now. The fact that a single writer might go and um, send information to multiple readers. Look at that examples. So why might we go in? We don't have to go to Google Docs. Google Docs assumes that there's multiple people writing also. We can just go and take just regular Google search. We assume that there's only maybe one writer here, and we can assume that the server is autonomously going and just reading some data from the file and changing it periodically, so we don't doesn't have to even to talk to another process. But Google Docs is a good example. We look at that in depth later. And there are multiple people interested in that state. Okay, so the reason here is sharing. There's many reasons to have multiple readers of state. One is to just allow them all to go and share some common state, okay, which may be changed by the writer autonomously without having other writers talk to it. Okay? So if you're sharing with text, sharing images, that's a good example, right? And um, Leo mentioned that we might want to replicate state to cache it. And that would be true if we went from the writable server directly into the clients. But generally, the server doesn't know which clients are connected to it, may want to connect to it later. It does know what clients are connected to it right now, but it doesn't keep track of the clients afterwards, after they've disconnected. So it can't just push data to them and say, hey, you cached this last time, you used this last time, so let me update your cache. But what it can do, and this is what happens with Akamai, it can write it to some mirrors that are that are geographically dispersed. So then a client that's near, that needs to get that state, that logical state that's physically replicated here, gets it from some mirror that's near it for performance reasons. Okay? So that's another reason. And of course, fault tolerance was mentioned and security was mentioned with blockchain, that we want to just make sure that we don't trust the various copies of data. So we go and um, take some kind of vote to decide what the true value is, as in blockchain. So these are all good reasons to have multiple readers of the same state. So this is sharing with performance. Okay, now let's make the scenario more interesting, and some of the examples you mentioned can reappear now. So let's have bidirectional arrows now. Okay, so let's assume there are multiple there are uh, multiple processes which are keeping their state consistent. Okay, so now these processes that I show, the clients that I show, are connected to each other, and they're logically all connected to each other, but physically they go and talk through a server. Okay, this is an architecture you find in many applications, and we've seen already examples of this, but let's just go and repeat those examples in this context. So familiar real world examples here. Okay, so Google Drive, as Jason mentioned, we have a server that keeps state, and we have clients that go and replicate that state. Right? And why replicate? We have answered this question to some degree, but let's just go and review that. Why do we really want state to be replicated in Google Drive? Let's think of all the reasons, some of which we might have seen, in fact, all of which we might have seen already. So we get reliability, backup. We get performance by having a cache on a desktop, and we get sharing, as Chris mentioned. Okay, so we get all these three benefits. And now let's go to Git. Okay, what extra thing do we get from Git that we didn't get from Google Drive? And I expect one particular student to answer this question for sure, but maybe there are other students, and that student's already raised his hand. So, Chris, so we get versioning, and then we have to merge also. Okay. Okay. So let's look at Git. Um, we've looked at sort of why we might want replication. Let's just get into the mechanism a little bit. Okay. So what exactly is communicated when we are using Git? And what is communicated when we are using Google Drive? What's the difference? There's a fundamental difference. And let's try to understand, let's try to distinguish between these two systems based on what is communicated. So Git is communicating diffs between files. Okay. Um, um, if there are, Git does allow images to be stored. So for images, it probably doesn't do the diffs. Okay. But for text, for programs, it certainly does diffs, and it's sort of diff centered. Though it can take images, we assume they're diffs. Whereas in Google Drive, it could do diffs, but I don't think it does. But it's fundamentally designed for arbitrary data. It's not targeted at textual data or programs, so it sends snapshots. Okay. Let's get to Google Docs. What do you think Google Docs is communicating? It's not diffs, it's not snapshots. What do you think it's communicating? Okay, so again, the key to understanding what Google Docs sends is to understand how versioning works there. So it doesn't have explicit versions, it has undo facility. And as I mentioned to you guys when we were looking at an IO manager, there are these notion of command objects, which are objects that encapsulate commands. And so undo is done by storing commands in a history and in a log, if you will, and executing undo and execute operations on it to undo and redo, because with undo we also have redo. Similarly, what it sends update the server is also commands. So essentially, this is log-based consistency. So the uh, the client generates a sequence of actions in a log, and that log is essentially replayed in the server. Okay. So if I insert something, then delete something, then insert the same thing again, then delete something again, and do this 100 times, we'll go and get 100 pairs of such commands sent to the server. If I was doing Git, I'd send nothing because I had probably, because I deleted everything I inserted. Okay, so the diff would show nothing. So there are pros and cons, but basically we're getting command logs. Okay. So each of the client and the server are both state machines essentially, and they make transitions from one state to the other based on received commands. Okay. So that's what's happening. So I've been telling you guys that um, you guys are creating replicated objects on your assignments. That's what I put in the assignment header always. So how does your simulation example compare with what we've seen so far? What is the closest, or let me put it this way, as this slide says, why is Google Docs the closest to what you do in your project? Oops. Well, I thought that was supposed to be student discussion. But anyway, you're also sending commands there, right? So you're sending the move command and other commands. So that's also a log-based uh, technique. And what you've got there is not, the server is not keeping a replica of the state in the case as Google Docs does. In your example, the server is just relaying commands and keeping these guys connected. So this is whole notion of read-write server versus relaying server. Okay, and so you're almost like Google Docs, except that Google Docs actually is extremely complicated. We won't even get into the consistency algorithm Google Docs has. Um, there's another course I teach where we discuss this, but that's a graduate level course, and I'm not sure when I'll be teaching that again, next. So, but the architecture is different from our simple architecture in the project because um, the Google Docs server is read write, whereas we've got a relaying server. But in both cases, we are sending commands. Okay, now you can send the move 50 minus 50 command You can send this pick take command and the give command, or you can execute. And for those of you who've done assignment 5, um, the IPC command which says my new IPC mechanism is RMI rather than gypsy rather than NIO. So I'm going to say that these two commands are fundamentally different. Okay? And let's try to understand what the differences are between these two kinds of commands, what makes them fundamentally different. The take and give commands are in this category, and IRMI is a different kind of command. And what is the difference? And this is kind of a subtle question, but the way I've phrased things in your assignment, you might be able to answer this question. And the key is uh, to go and try to understand what state these commands are changing and what state this command is changing, and what's the difference between the two kinds of states. Think about that. What I have. So there's a primary and application specific state that we want to keep consistent. Okay. To achieve consistency, we need to create some new state in our mechanism, okay, which is the replication mechanism state, which I'm going to call the meta state. Okay. And if you notice that in the assignment, I call that meta state IPC mechanism. So to achieve consensus of some state, we need to create some additional state, okay, some additional meta state. And we are trying to achieve consensus about the meta state. Okay. So, the meta concept is used a lot of places. So every object has a class, as you know, in object-oriented languages. And a class describes objects, and a class itself has a class. So the class describing a class you would call a meta class. Okay? And Java doesn't make that evident. It just says all classes inherit from the class. But in Smalltalk, which was the first language to treat classes as objects, there was a notion of metastate. So whenever you defined a class, you defined, and in effect, the class methods are the ones describing the behavior of the class, and the instance methods are describing the behavior of the instance of the object, the primary state and the meta state. Okay, so we are trying to achieve consistency of meta state. Now, making the IPC mechanism variable is very quite peculiar to our project. Not, systems just go and focus on one IPC mechanism and just stick to it. But since this is an educational project, I want to give you experience with using multiple IPC mechanisms. So we've got multiple IPC mechanisms. Of course, then we need to keep them consistent. So let's look at some meta state that people may actually want to replicate. Okay? And think of that. Think of some state that is needed to achieve consensus between different states. And then let's complicate the matter also a little bit and allow the same state to be changed by multiple writers. We've kind of punted on that issue. We just hope nothing bad happens. So think of some state that you might create to prevent bad things from happening. So by the way, later we will go and have multiple consensus mechanisms also, and we will allow the consensus mechanism itself to be shared. So we need consensus on what the current consensus mechanism is. Okay, so again, this is sort of a bootstrapping recursive idea. So think of what we are using right now. Let's assume we've got a shared screen, and think about what and imagine that right now I'm the only one manipulating the slides, and we are doing slides. Let's just take Andrew's example of studying for 550 using a whiteboard. Okay, and assume that we don't have a custom whiteboard that allows sharing, which makes life easier for the user. Let's assume we took a drawing editor that was not collaborative, and we just shared it using Zoom. Okay, so we are sharing a regular whiteboard that's not designed for a regular drawing application that's not designed for collaboration, a collaboration unaware um, drawing application, and sharing it using Zoom screen sharing mechanism. And multiple people can be arguing about something. So you want some consistency if we are trying to go and right at the same time, bad things can happen. And think of some state you might create to prevent such a bad thing from happening. So meta state to reduce conflicts, not to cure conflicts. Cure conflicts means doing some kind of merging to reduce conflicts. Okay, so if you were to, sorry Akshay, I saw your hand late. Okay, did you have something additional to add? Okay, so we're going to have, if we had, I told you guys that if we had a custom whiteboard, then we can lock every circle and every oval and every piece of text, so that I can be adding a piece of text while you're editing another piece of text. But if we have a shared desktop system like Zoom, then we would lock the application, and we would have what's called float control. Okay, so now we can have a timeout and say, hey, you can only study in this room for 30 minutes, and then, like David said, we can have a scheduling policy that decides, okay, the next person goes in. But the first group that entered a room can just lock the room literally until it releases a lock. Nobody else gets to go in. Similarly, we can have locking in these shared desktop systems. And just to give you an idea of what bad things can happen without float control, in all of these cases where you're taking existing applications that don't even know that they are distributed or collaborative, and we sharing them collaboratively. So what happens is they get a set sequence of events that they assume is coming from the same user, which end up coming from different users. Okay, so I can begin a drag, and you can complete it. Okay, so I can click the mouse, press the mouse down, I can drag it, and before I release it, you release it. You somehow create the release event. So that will go and complete my event, and then my extra release button is something unexpected. And for you to have generated the release event, you must have pressed the button too. So you can get two successive press buttons and two successive release buttons, whereas a single user application would never get that sequence of events. Now, some Windows systems can deal with that perhaps, but the system that old timers like me worked with was a system called X, and X would crash if that happened. Okay, so you can get event sequences not possible in single user application, and and crash application in some Windows systems, not some applications in some Windows systems, windowing systems. So we have an example of a coarse-grained lock, and the previous, all the old systems I knew had flow control to prevent this problem. And I don't know what happens in Zoom. You guys, if you ever have time, just experiment with this and see what Zoom does. I'd be very curious. So flow control provides locking of applications, and it provides a very coarse-grained locking. It's like, I have 10 critical sections, and I just disable interrupts to make sure that no other process executes at all, and no other thread executes at all. So I get exclusive access. I can't have multiple threads accessing multiple independent critical sections. Okay? But the idea of locking is not is not peculiar to is not tied to force control. And so what's happening here is that lock state itself must be replicated. Okay, we should all have an idea of who's got the lock. So we should have consensus on the lock state, in addition to having consensus on the state we are sharing. Just as we need consensus on what IPC mechanism to use to go and replicate our Halloween simulation state. Okay? So this is an example of meta state being replicated. And here's file locks. So and this happens to me all the time when I use Google Drive. That as I'm saving my file, and the files can become 100 megabytes when I'm saving audio, the Google Drive starts trying to read it while PowerPoint has not finished writing to it, and that causes all kinds of problems. I might have mentioned this earlier, so I always go and copy my PowerPoint to my desktop. I give my lecture, I save the file, and then I copy it to Google Drive. So that's finer grained than the whole screen, but not as fine-grained as, say, locking parts of a whiteboard. Okay, so let's look at the Akamai architecture. Okay, I have a server into which I can write data, and there are mirrors, okay, which don't go and put data back into the servers, from which we can retrieve data. And in this architecture, what happens if the server dies? Okay, and how do we need to change this architecture to allow fault tolerance? Okay, we're not necessarily interested in sharing, but in fault tolerance. And let's go and think of a solution that doesn't add new processes. I know we are in distributed computing, so we want to add new processes. Before we add new processes and motivate them, let's go and try to think of something we can do that might create some downtimes, okay? But that does allow us to eventually recover from a fault, okay? So we're going from Akamai architecture to, we went from Google Images to Akamai architecture. We went from Akamai architecture, which is meant for sharing with performance, to share to um, and the sharing occurs only if you have multiple. Yeah, the sharing occurs off a particular server, and it may or may not have multiple agents writing to it. So we don't want to add new processes, and we do want to recover from this. So what might we be doing to allow that to happen in the server? And think of some application you may design. So we assume there's some log file, okay? And whenever somebody writes to this server, we're assuming here only one writing client. And like I said, the server could just write on its own also. There's a log file kept in some state that persists, and we want a stronger guarantee than persistence. We want what's called stable storage. Okay, stable storage is guaranteed to not be lost. Okay, so disks can crash, and it's impossible to build stable storage really, but you can try to go towards stable storage by, for instance, replicating the disks, having a RAID system. Okay, so so when the new server, so when the server goes down, a new process comes in, it goes and reads the log file, and then the new writing client can contact it, and it can then go and send data to the mirrors. Okay. So what happens if there are log file errors? Like I said, we can try to create stable storage by having multiple disks, but I put the stable word stable within quotes. And master corruption or stable storage error, what happens if that's a problem? And so we had these slaves that were just accepting data. Now we allow the states, now we do what he was talking about. The server goes down, the master goes and says, hey slave, give me what data you have. And it doesn't trust the slaves too. This might be David's situation, that there may be some um, might be a Byzantine situation. Byzantine situation is when some processes are maliciously giving you the wrong information. We so far assume that processes behave, they may not behave. Okay, so it can get it from one slave, it can get from another slave, and it can read from the log file. Okay, and then it can go and decide, it can take some kind of vote and said, okay, there's agreement on this value. So we have an odd number of agents here to get data from. So whatever is the majority, I will assume that to be the correct value. And or it might want unanimity. But you know, in spaceships, there's fault tolerance. There are multiple computers trying to make this compute the same thing. So there's often consensus used to go in, some kind of voting used to ensure that we can agree on the same value. Okay. So now when the writing client goes to the master, it goes in, it can go in, uh, it can go and uh, continue doing what it was doing earlier. Okay. I'm trying to go and move around the participant window so that it doesn't obscure my slides. That's why you see sometimes a delay before I go and speak the next word. Okay, so in this case, we are willing to take some downtime. Okay, the master, when it comes up next, it either reads from the log file only or it reads from the slaves also. And but till it comes back up, uh, the reading clients are in, can't get the data. So how can we modify this architecture and this protocol to make sure there's no downtime? So think of how you can vary this picture. And some of you may already mention this, I forget, but it's not too complicated to change, that we don't want any downtime. We want to continue work till while the machine is down here. And the key is that we've got now multiple. Oh, well, I was supposed to have a slide there, I thought, but I guess I don't. So let me just give the answer. So the process goes down. Now another process becomes the master. So the writing client contacts that master. Okay, so a slave became a master dynamically. And when this other machine came up, it came up as a slave. And so we changed roles. Okay, I'm surprised I didn't have a question there, or I just forgot. So we are gradually making the slaves, the Akamai mirrors, more and more sophisticated. First, they could only receive data. Then they could go and give data, but they couldn't take the role of a master. And now they can even become masters. And with this architecture, it's unfair to call this the Akamai architecture at all. This architecture is fundamentally different from the Akamai architecture, and so was the previous architecture, to be honest. So let's go and ask this question. Supposing I come up with this architecture or the one before it, do I need Akamai? Or I'm kind of arguing that the Akamai situation is very different from the slave master situation. Whether a slave becomes a master or not is a small deal compared to the fact that a mirror becomes a slave. Okay, so a mirror just receives data, a slave can give data, and a slave can not only give data to an old master, but it can also become a master itself. So I'm arguing that there are fundamentally different reasons for choosing mirrors and slaves. So what are the different reasons? Maybe what you do underneath is similar, but there are different reasons for choosing one or the other. So with Akamai, synchronization time can be, with that architecture, the whole idea is to go and put mirrors very far away from the uh, main server. So synchronization time can be high if slaves are on the edge. And what we want typically is the slaves to be very close to the masters. And so we want them in data centers. And so synchronization time is low if slaves are in master's data center. And slaves are fundamentally there to provide fault tolerance and read load balancing rather than edge performance. Okay, so they can also provide some kind of, they're providing load balancing, that you're saying, okay, this particular server in this location is too overwhelmed. So we will have, because people in this area are accessing it quite often, very frequently. So we're going to basically have multiple processes that can answer the question. Okay. So they are in master's data center, and multiple data centers for some. And so the data centers can be protected, physically protected. So that improves security also. Okay. So that's typically what you will have. Now, can you imagine having multiple data centers for some service, each with its own master? And maybe think Facebook. Okay. So the situation's somewhat under control as long as there's one master with a bunch of slaves. Okay. And like I said, if there's a lot of traffic in North Carolina, then we can have, or let's say there's a lot of traffic in California, then we can have a master with a lot of slaves there. And if you're talking about North Carolina, we might have a master with a few slaves. But can you imagine having, um, for the same service, a data center in India, a data center in China, a data center in the US, with multiple master, with the master in each data center? That's going to cause some problems. So we ideally don't want to have multiple masters because then we can get into conflicts. Let's assume conflicts are somehow magically resolved. We have some kind of lock control, um, and we'll see other techniques that we can use to go and delegate services to the masters. So, and think Facebook. Why might you want to replicate data? Why might you want multiple masters, and why might doing so not cause conflicts that we need to worry about? Okay, so Facebook doesn't have any kind of concurrency control. So I'm arguing that in Facebook you can have multiple masters in different data centers and yet not worry about uh, conflicts if we make some assumptions about which master a particular client contacts, and if there's a well-defined way to go and determine that mapping. Okay? I'm not sure I'll be able to retrieve the answer from you based on these hints, but I see 3 hands, so good, good. I might have explained the problem enough. And think of geographically dispersed rights, like I talked about, India, China, and the US, and also um, assume that so we can have multiple writable masters, okay, and they can replicate the whole database, in which case we need some conflict resolution or avoidance scheme, or they can have partitioned data where each master is responsible for part of the data, and a uh, client knows which master to contact based on what data it needs to access. And multiple masters can provide write load balancing, and and if we replicate the whole data, then we can have power failure tolerance. Okay, now a lot of these data centers have generators, but at some point that may also become an issue, and with lockdowns, who knows what can happen in one region of the world, and so we want some redundancy. um, and multiple masters can provide edge performance for geographically dispersed rights. And so what kind of conflicts are possible? So I posted a message. Only I can post the message. That's good. But there are multiple people who can go and comment on that post. And we can have conflicts there. But if we assume those messages, and I don't know how Facebook deals with this, but if we assume those comments are a set rather than a sequence, okay, then we can tolerate different people seeing those messages in different order. Okay, so that's one issue that in a Facebook-like system you'll have to resolve. Um, so again, a client goes and writes to home or nearby data center. If it's nearby data center, then we can have conflicts. But if it goes to the home center, we won't have conflicts of certain kind. But we can have other conflicts possible, and then we can have conflicts still where these are not sequenced writes associated with some account. Um, Two people try to create the same account, somebody in England and somebody in America, both want to create an account called Smith, and which Smith is the first one chosen. Okay, so we'll need some centralized location to do that. And you can imagine these masters that they contact go to an appropriate master to go and deal with this infrequent occurrence. Okay, at some point maybe the whole world will be using Facebook, so there won't be any. Only when new people reach the correct age will new accounts be used. But in general, creating of accounts is far less frequent than accessing shared data. Okay. So we saw that when we had possibly malicious slaves or uh, corrupt slaves or corrupt files, we needed voting. Okay, we couldn't just go and unilaterally say, here's a value, everybody accept it. Okay, we needed to have some kind of voting. And in your last assignment, you're going to do this kind of voting. what are some other examples of voting? And I'm not sure whether I'm asking you the question or I'm just giving you the answer there, but let's see what I go to next. Oh yeah, I think I ask a question here. So think of going to Travelocity or Expedia. I think this is Travelocity. I forget which one I'm using. And I'm trying to book a flight for my onward journey. Trying to book a flight for my return journey. I'm trying to book a car in the good old days when I didn't have Uber, and I'm trying to book a hotel. So I go to some server like Travelocity or Expedia, and I'm claiming that this particular transaction, and I'm going to use the word transaction, just as you had a transaction when you went and submitted your quiz to Sakai, this transaction requires some kind of vetoing possibility. So why is that the case? So between David and Chris, you sort of both pointed out reasons for voting. So basically, this logical server you're going to is talking to multiple other servers. That's why I've colored them all differently. There's the airline server, there's maybe multiple airline servers, there's a hotel server, there's a car rental server. So before you can um, um, before Travelocity can show you the results, it needs to go and check with each of these servers whether what the user is asking is available or not. So they have vetoing capability at that point. Okay, and then when you get to decide to commit, and at that point you can choose. And then when you get to commit it, things might have changed because, and this has happened to me many times. So if things change, if you're lucky, Travelocity will go and say, sorry, your transaction could not be completed. This happened to me once. I was trying to book a flight to San Francisco, and it said, sorry, couldn't do it. The flight is $500 more expensive. And then I said, oh, let me try it again. And this time it succeeded, but the price it gave me was not what it had presented earlier. Okay, it gave me $200 more than what I had asked for, and it just committed it. Fortunately, there are non-technical ways to solve this problem. Travelocity gives me 24 hours to cancel the flight, so I could have canceled. So there's two kinds of vetoing possible. One, initially, and secondly, when you want to go and commit, when you've chosen a value and you want to commit to it. So there's this notion, and this is similar to the problem I started off with, where we propose a change to the course and we have to accept. We have a voting to decide whether that proposal accepted or not. We're not just unilaterally going and saying, here's a new value. Okay. So this is an example of what's called in uh, distributed system nested transaction. That I'm making a transaction that has sub transactions here, and this parent transaction finishes when each of these transactions finishes. And that's a very complicated and interesting field, which I've talked about in my graduate courses, but which we won't talk about here. But at least we should know about the need for nested transactions. Okay. I think I have the replicated slide here. Okay, this is perfect. We are 2 minutes away, and that was just an extra slide. So here's a text-based summary of what we looked at. We looked at browser Sakai notion. We looked at Travelocity with nested transactions. We looked at Git, Google Drive, OneDrive, and Google Docs, and saw the differences there were. We saw meta and regular state or configuration state. We saw physical mirroring. This is not in the sequence we went through material. And the mastered processes are often called primary processes, and the slaves are called backup. Primary and backup were these sort of academic terms used initially, but today the industry is caught up with academics, and they typically use master and slave. And we saw master replication also. Okay, so we've got a nice overview of how consistency architectures what the consistency architectures might be. We don't have a good idea of the algorithms, okay, but we have an idea of what the architectures might be, what the scenarios might be. So we are going to go next into specific algorithms. Okay, and we'll see how difficult they are. Okay. So last time we looked at various scenarios in which we might need consistency, and I need to add to those. Okay, one more scenario, and let's look at this architecture, which is a general architecture for many things we saw, where you have a bunch of clients talking to a server. The clients could be, and the clients could be real clients of some service. They could be end user clients, or they could be slaves of some master that keep track of all the changes and can later become masters, or actually can give a failed master some data. Or they might be distributed masters talking to a centralized master to go and serialize certain kinds of changes, as we saw in Facebook. Account creation might go through a central master. Okay? So we have this server here, which might be just a master, a master, or it might be a slave that became a master, or it might be just a relaying server, something that just simply communicates messages among the clients and does not keep any state at all. Okay? So this was a general architecture, and I'm going to argue that to achieve the same functionality as this particular architecture is giving you, we can have another architecture. Okay, so we want to keep the same functionality. Let's say we've got a bunch of mirrors. So these could be mirrors also, by the way. I didn't mention this here. This could be client, save, master, or a mirror. So these could be mirrors keeping some state, or they can be slaves, or just think of Google, good old Google Docs, where this is an end user client, this is another end user client, and they're keeping the data consistent through a Google server. Okay. So let's take this Google Docs example more thoroughly. Let's say that we want to do Google Docs just to make it more concrete. What's an alternate architecture that could also provide you with some consistency of your documents? And that alternate architecture essentially involves drawing arrows differently. So we can have everybody going through a central process, or we can have peer-to-peer communication where every replica talks to all of the other replicas. Okay, so that's just drawing the arrows differently. So that was the easier question. The other question is also not so hard that follows this. So given that there are alternatives, and life becomes more interesting with alternatives, how do you choose among these alternatives? Okay, and there's no one right answer. So the question is, what are the pros of this and cons of this, and which of these cons are pros of this, and which of these pros are cons of the peer-to-peer architecture? Okay, so I'm sure you guys will come up with many things that I haven't thought of. So let's go to you guys first. Okay, so what is the advantage and disadvantage of P2P versus server-based? One of the advantages of server-based is that the clients can be aware of the server, and the clients don't have to be aware of each other. Okay, so that's something you guys didn't mention. As Jason said, the conflicts are ordered through servers, so things are easier. Things are much harder in the P2P case. Specifically taking Google Docs as an example, I can't tell you as an editor, because I told you I work in this area, how many papers have been proposed here that go and find bugs in the previous algorithms, in the case of, when they try to do P2P algorithms, whereas centralized is much easier to get consistent. Okay. You guys didn't mention this, but one of the reasons we like servers is because they're always online and backed up. Okay. And Randy mentioned that, look, when you're reading data, you're guaranteed a certain amount of time to get the data. So there's a performance advantage. And there's also a performance advantage when you're writing to a whole bunch of people. So let's say you're giving a talk that's being broadcast to the whole world, and these days that makes sense. You're giving the State of the Union address through Zoom. If you're let's say you're doing it through a low-powered computer, then that computer has to go and multicast to the whole world, and your computer will be spending all its time multicasting rather than going to the next slide. But if you go and delegate that work to a server, it could do it much faster. Okay? Chris mentioned security. So somewhere here, so indeed, what you said is right, that when you have a server, you know, who can modify can be better controlled. But we can imagine the access control tables also being replicated, and we can imagine them being replicated in such a way that they can't be corrupted. And we can imagine also having some kind of encryption keys. So you could take care of the authorization problem even without a server, but server would certainly make that easier because the meta state of our collaboration, which is access control, could be kept in the server. Okay. So you guys didn't mention this, but again, going to the Google Docs document, I told you there have been many papers on the subject, and one of the authors of these papers, who's the most zealous about this architecture, is a guy who lives in Australia, or who lived in Australia. He's now in Singapore. And if he has to collaborate with somebody in Singapore, and the server is in the US, then messages have to go through the US server to reach the Singapore person, okay, or to the China person. And you'd say, how big is the delay? Well, if you just look at the speed of light, that's a sizable delay. Okay, so he has been the biggest advocate of P2P collaboration, and um, you know, I said that look, security might be better with the server-based architecture for the reasons Chris gave. Also, but there's also reasons to believe that the P2P architecture would have fewer privacy concerns. So today, with the coronavirus problem, we do want contact tracking, but if that contact tracking information is kept in the server, then there is more chance that even if it's encrypted, things could go wrong, and your privacy could be given away. Whereas with the P2P architecture, if the information is being kept only with you, um, then the problems are fewer. Now, how you can implement, again, you'd have a multicasting problem if you have to go and track everybody else who's come near you if you fall sick. But in general, P2P has fewer privacy concerns because you're not giving information to a server. You don't have to set up an infrastructure. So if you just want to have an ad hoc collaboration among people, you built a nice collaborative application. You don't have to go and install a server and go and give everybody access to that. You can just, four of you in an airport can just go and collaborate with each other directly. Okay, so that has been a big reason for P2P also. And as two of you wanted to say and one of you said, there's no single point of failure, okay, which is a very big deal in consistency. So basically there are pros and cons, and I don't think I've fit all of them here, but here are some representative pros and cons, and they're both good architectures to study. And in terms of, you can mix the architectures in many, many different ways. And one simple way is that if you don't want the clients to be aware of all the other clients, you could have a setup phase where you contact a name server, discover each other's addresses, and then you go and communicate directly with each other. And there are many other ways to do hybrid architectures. So P2P for write communication. Okay, so this is important that we looked at many scenarios, and I realized I hadn't gone and touched on this one. So we add to the set of scenarios we saw earlier this particular architecture and scenario.